Hello everyone, I'm Haoren. I will discuss Net-P4ct system, which enables enhanced WAN bandwidth fair sharing with P4 program switches. I'm presenting this talk on behalf of my coworkers. First, let's look at the challenge we have. Driven by applications including cloud services, live streaming, and on-demand videos, etc., the capacity of ByteDance self-built WAN has increased from 010 to 000 terabits per second in the past few years. Due to the long deployment cycles and high provisioning cost of WAN expansion, network operators strive to improve bandwidth utilization and resource efficiency in order to meet the SLOs for various applications. We generally categorize the traffic classes into high priority and low priority class. We observed that each class consists of diverse service type. A few infrastructure services such as compute and storage and main business applications account for majority of the network traffic in each priority class. A large fraction of low priority traffic belongs to distributed file system, which exhibits bursty traffic patterns. It is important and challenging task to enable effective bandwidth sharing for a large number of services. One unique scenario in our backbone network is the mixture of traffic originated from heterogeneous types of sources, such as self-managed data centers, CSPs, and the internet. Based on our service scenario, backbone traffic is categorized into two types, host-to-host and external-to-host. Host-to-host means traffic originates from internal to internal servers. External means traffic originates from cloud services or the internet to internal host. For example, load balancers are deployed with a third-party cloud. These load balancers forward traffic through our WAN to backend servers in remote data centers. This approach enables flexible and fast workload expansion and leverage our WAN to deliver more optimized performance. In this figure, we can see that an average and peak traffic ratios of different traffic types in one of our backbone regions. Clearly, X2H traffic is an important scenario in our network. To tackle this, inspired by previous work, we have deployed a host-based daemon on each server named Net-Agent. Net-Agent utilizes eBPF program in the kernel to implement a set of functionalities, including host traffic monitoring, packet header modification, and traffic throttling. With a central control plan and inventory system, it can work with our containerized infrastructure. However, such a traffic throttling design has several challenges in practice. Challenge one is throttling is consuming CPU cycles heavily. Based on our operational statistics, 1 million host agents will consume approximately 0.20K CPU cores. Challenge two, we have more than 50 kernel versions deployed among millions of hosts. It brings up tremendous operating and maintenance cost. We have encountered incidents due to kernel version difference. For example, in one kernel version, packets are mistakenly marked with a large timestamp. The bug was later fixed in kernel version 5.10. And challenge three, traffic from blind spot. Due to the X2H traffic in our backbone network, part of the network traffic cannot be captured by host agent, causing blind spots. So we argue that the component should locate on a critical path of all types of WAN traffic. The next question is, what about conventional network devices, such as PE switches, like this? Can we do bandwidth enforcement in PE switches? The answer from our standing is no, because PE switches can only provide limited flexibility as switch fabrics are optimized for traffic forwarding. In addition, frequent changing device configurations is not ideal for maintaining network stability. Therefore, we introduced Net-P4ct. It is a WAN-wide bandwidth management and enforcement system across distributed data centers. At each one ingress point, we deploy dedicated clusters consisting of P4 switches. All traffic, including that from host, cloud services, or the internet, is processed by the attached P4 switches before being redirected to its destination over the WAN. Net agent now only tags live packets with a service identifier. This allows P4 switches to recognize the traffic source at line rate. A typical workflow of Net-P4ct is first we receive user-submitted bandwidth request. We will evaluate based on our available bandwidth resources. If this request is accepted, Net-P4ct will install policies to P4 switches for in-network enforcement. Here we take a quick look at the bandwidth request model abstraction. We define a job as the minimal unit of bandwidth request, represented as a tuple, job ID, service pattern, region A, region Z, guaranteed bandwidth, wait. Each job corresponds to a collection of flows from a source region, region A, to a destination region, region Z. A single business service typically consists of multiple jobs. The pattern fields describes the traffic characteristics of the job, but classify patterns into two categories. Similarly, host-to-host pattern. In our containerized infrastructure, multiple services share the same computing resources. To distinguish traffic at the job level, packets originating from hosts are required to carry a unique job ID. This ID can be recognized by P4 switches and used to associate the traffic with the job. An external to host pattern. In our scenario, we identify such traffic using a three-tuple pattern: source IP prefix, des IP prefix, and protocol. For sure, we can extend to a five-tuple pattern, depending on the scenario. For instance, public IP address of a cloud load balancer is used in a service job. And the guaranteed bandwidth field specifies the requested value from region A to region Z. This value represents a strict guarantee. The network team should ensure the requirement is met. And the weight field indicates the priority level of the job. A higher weight indicates a higher priority. After bandwidth request is submitted, Net-P4ct determines whether the request can be granted based on current resource availability. Each link's capacity is divided into two classes: reserved capacity and non-reserved capacity. Reserved capacity is used for high priority traffic and guaranteed bandwidth allocations, and non-reserved capacities for best effort traffic and non-critical services. This is to ensure fault tolerance. We reserve a portion of the network's total link capacity as headroom to support disaster recovery scenarios. For example, consider a scenario where 100 giga links connect region A and region Z, providing a total capacity of 400 G. To maintain resilience, 60 of the total capacity is reserved, and the remaining 160 G is classified as non-reserved capacity. When users want a guaranteed bandwidth, they're always reserved from the reserved capacity pool. Net-P4ct's objective is to maximize overall network throughput while having this constraint. First, it should be work conserving. That means one job can use spare bandwidth beyond its minimum guarantee when a network is underutilized. This helps us to make the most of the network bandwidth resources. The second, while guaranteed bandwidth specify the minimum request, fair share bandwidth reflects the additional bandwidth a job may receive based on its priority weight. Number three, we use weighted max-min fairness model, and we calculate fair shares using the water filling algorithm. More details can be referred to the paper. After allocation is done, next step is bandwidth enforcement. Our operational experience reveals that rate limiting introduces throughput fluctuation. This is due to threshold-based enforcement. Rate limiting is activated when link utilization exceeds an upper threshold and is released only after it drops below a lower threshold. This behavior results in repetitive swing in throughput, reducing overall bandwidth utilization efficiency. This figure shows this phenomenon in our production network. Rate limiting was triggered at time T1 when link utilization reached 80% of the capacity. It remains active until T2 when the throughput fell below 65%. A similar cycle occurs from T3 to T4. To address these limitations, Net-P4ct replaces rate limiting with DSCP remarking performed by P4 switches. Downstream WAN switches enforce QoS policies based on DSCP values using strict priority queuing. To tackle this, we propose two enforcement policies. The first one is a meter-based policy. It's intuitive to understand. We provide a two-ray three-color marker for each job to classify packets into three priority levels: green, yellow, and red. For simplicity, it can be conceptually modeled as a cascade of two token buckets. Every packet sequentially passes through both buckets. For clarity, we'll focus on rate-based behavior and omit burst size considerations. Each meter is configured with 4 parameters. If we ignore the burst size considerations, we will have 2 parameters: committed information rate, CIR, and peak information rate, PIR. In our design, CIR is set to jobs guaranteed bandwidth, while PIR is set to the sum of guaranteed bandwidth and fair share bandwidth. Packets are then remarked with DSCP values and mapped to switch queues as follows. The green will go to high priority queues class, and yellow packets will go to medium priority queue. The red will go to low priority queue. While this method is intuitive, its per packet operation can cause packet reordering at the destination. To address this, we introduce statistics-based policy. It operates at the flow group level. We can see from the figure, a statistics-based policy consists of 2 components: manual coloring and burst mitigation. It works as follows. Traffic flows are mapped into a set of hash buckets based on their hash values, with each bucket representing a flow group. A feedback mechanism monitors the real-time throughput of each bucket and updates its DSCP value periodically. We select a subset of buckets such that the sum of their rates meets or just exceeds the guaranteed bandwidth. It's like a variant of knapsack problem. While manual coloring can eliminate flow reordering, it cannot respond quickly to short-term traffic bursts. To address this, in burst mitigation part, we deploy 2 additional meters, one for green packets and one for yellow packets, to enable fine-grained burst detection and prevent potential overload. For green packets, the meter is configured with both CIR and PIR set to the guaranteed bandwidth. Thus, traffic within the guaranteed rate remains green, while any excess is downgraded to red. And similarly for yellow, any excess is marked red, and within this red, it remains yellow. We take a very quick look at the evaluation part. We evaluate the effectiveness of the statistic-based bandwidth enforcement policy. 3 jobs share the link. Each has its own required bandwidth and weight. In each phase, the actual throughput of each job varies. I quickly summarize the figure 1. The required bandwidth is guaranteed by Net-P4ct. All 3 jobs, their required bandwidth are guaranteed by Net-P4ct, and also the additional link capacity is shared among 3 services. We also test the CPU overhead. The figure shows that as the number of flows increased from 2,000 to 16,000, the CPU usage for both modes increases, while Net-P4ct remains under 3% CPU usage, even at 16,000 flows, and host-based throttling is reaching near 15% CPU usage. This means Net-P4ct can reduce the CPU usage a lot. Next, I will share our deployment experiences. First, bandwidth request reviews are essential. In a fast-paced environment where new services are launched frequently, oftentimes their initial traffic patterns are unclear to network operators. It is crucial for the network team to collaborate with service team to continuously review and adjust bandwidth requests, especially during early deployment. Based on our operational experience, service team often overestimate their bandwidth needs, leading to inefficient resource allocation. To address this, if the usage is far less than the requested, the service team is responsible for a fixed portion of the cost. And next is cluster scaling out. Our system exploits a cluster of P4 switches to provide both high availability and load balancing. If the service traffic is below a predefined threshold, empirically set to 1 giga, we will encapsulate the packets into a VXLAN tunnel and steer them to a single designated P4 switch. The enforcement policy is applied on this single switch. When a service traffic exceeds the threshold, we distribute the policy enforcement across all switches to leverage the aggregate processing power of the cluster. Third, failure detection and fallback is critical. Since P4 plays an important role in Net-P4ct, we deploy active probes that monitor both P4 and non-P4 paths simultaneously. This allows us to quickly identify the source of failure. In the event of a P4 switch port failure or an entire P4 switch failure, the BGP routes are automatically withdrawn, so it can be seamlessly redirected to the other ports or device in the cluster. In a highly unlikely event of a catastrophic P4 cluster failure, we have implemented a fail-safe mechanism to ensure basic network connectivity. So it allows us to bypass the entire P4 cluster by falling back to the underlying physical network. The last one is deploying Net-P4ct outside ByteDance. The core concept of Net-P4ct is actually a general in-network bandwidth sharing mechanism, and we are actively exploring the feasibility of porting Net-P4ct to other prominent networking silicon, such as Triton 5. Okay, to conclude, Net-P4ct provides generic and flexible network bandwidth management approach, and we implement an efficient bandwidth enforcement system that integrates a controller with P4 programmable switches. It's work-conserving, guarantees per service minimum bandwidth, and provides maximum fairness across all services. And we share our deployment insights and operational experience in real-world production network. Thanks for listening. I'm happy to take questions.